All right, welcome back to GLS4OM. Still continuing work on our matrices unit, which will help prepare us for our first-year university courses in linear algebra and any course that requires linear algebra in order to solve. Today we're going to be looking at types of matrices, but the most important thing we're going to do in this particular lesson is learn how to operate on matrices, how to multiply by scalars, add, subtract, and multiply. There's no division for matrices. As per usual, we'll start with a little humor, so I'll let you read that Foxtrot comic for the day. All right, so hopefully that was enough time. If it wasn't, you can pause. So we got the square root of 9 ounces, counting up to the square root of 36, to the square root of 81 ounces, the square root of 144 cold, delicious ounces for Jason Fox. And Paige Fox's sister says, "You're a weirdo." And of course he says, "I take my root beer pouring seriously." Another one of those math puns. Perhaps you liked it, perhaps you didn't. I found that one mildly amusing. All right, moving forward. Types of matrices. So a matrix definition, and I probably should have done some of this stuff at the very beginning of the unit, but better late than never. What is a matrix? It's a rectangular array of numbers. So I'm giving you some examples here. The numbers in the array are called the elements, so I have been referring to these things as elements. A matrix that has m rows and n columns would be called an m by n matrix. The number of rows always precedes the number of columns, and the numbers m and m are referred to as the dimensions of my matrix. So something simple. What are the dimensions of these matrices? First time to ponder pause. All right, resuming. This probably wasn't too terribly difficult. You just have to remember rows first. 4 rows by 1 column, 2 rows by 5 columns. So 4 by 1 and 2 by 5. All right, what's next? A matrix with 1 row is called a row matrix or a row vector. A matrix with 1 column is known as a column matrix or a column vector. So this is our column matrix and this is our row matrix. I'm going to circle this one here because when you're finding solutions to linear systems and you're going to express things as vectors, vectors are going to be written in university using column vectors. All right, next, if a matrix has the same order, i.e. the number of rows and columns are the same, then it's called a square matrix, not surprisingly, of order n. The diagonal that goes from the upper left to the lower right is called the principal diagonal in a square matrix. And I've highlighted this one in blue, and I just showed you that one there in green. More definition type stuff. The elements are represented using a single letter with a double subscript. We've already reviewed that the previous lesson. The first number represents the row, and the second one represents the column. So first row, first column, second row, first column, second row, third column, and so on. Oh, and this might be new because I don't think I wrote this notation before. So you might see the capital letter A used to represent this matrix, or you might see equals, and then in square brackets you're writing A, subscript ij, and then this would be the dimensions of your matrix. This particular one happens to be unknown, so m rows by n columns. All right, now I'm going to get you to answer these questions. How many elements in a 3 by 5 matrix? So I'm not going to read them to you. I just covered a bunch of definitions. How about you answer these questions? Again, a time to ponder pause. All right, taking this up. How many elements in a 3 by 5 matrix? Well, 3 times 5 is 15. Not surprisingly, 15 elements. A square matrix has 16 elements. What's its order? Its order must be 4. It must have been a 4 by 4 matrix. If a matrix had 20 elements, what are its possible dimensions? Well, we're looking for factors of 20. We could do 1 by 20, 2 by 10, 4 by 5, 5 by 4, 10 by 2, or 20 by 1. Those are all the possibilities. Here is a particular matrix where I have given you the elements, asked you to create it. Notice all of these elements will be in the first row. And then these elements here will be in the second row. So 2, -3, 4, 0, 0, 7. My matrix has 2 rows and 3 columns, so it is a 2 by 3 matrix. Types of matrices, more definition-y type stuff. 2 matrices are equal if and only if they have to have, first off, they have to have the same dimension. 2 matrices cannot be equal if they don't have the same dimension. And not surprisingly, corresponding elements have to be equal. So these 2 matrices here, this one M by N, this one P by Q, will be equal if and only if M is equal to P and N is equal to Q, and Aij is equal to Bij for all I and J, I running between 1 and M, and J between 1 and N. So these two will be equal to each other. They both have the same dimensions. They have dimensions 2 by 3, and then every element that corresponds are equal. So A11, A12 is 4, A13 is 0 in both matrices, A21 is 3 in both matrices, A22 is 5 in both matrices, and A23 is 6 in both matrices. So these matrices are equal to each other. All right, a challenge question. Now that I've just given you the definition of what it means, these 2 matrices, and that got cut off. This is not the floor function. These are matrices. These 2 matrices are equal to each other. Find the values of x and y. Again, a time to ponder pause. All right, resuming. So we just discussed that corresponding elements would have to be equal. So x plus y would have to be the same as 5. Of course, those zeros are equal. These zeros are equal. And we would now have that x minus y needs to be 1. So I'm going to be solving this linear system. X plus y is 5 and x minus 1 is 1. Adding, I will get 2x is equal to 6. So x is 3, 6 divided by 2 being 3. Back substitute into the first equation, 3 plus y is 5, so y is 2. So if these matrices are equal, then x is 3 and y is 2. All right, more definitions, the zero matrix. So the zero matrix is a matrix in which all of the elements are 0. It will be known as, once we have its dimensions, the M by N zero matrix. The unit matrix is not a matrix in which all of the elements are 1. It is a matrix in which the principal diagonal is 1 and everything else is 0. Of course, that's going to imply it has to be square. It does say square here, but I didn't mention that initially. You only have principal diagonals in square matrices. This will also be called the identity matrix. So the unit matrix or the identity matrix looks like this. The principal diagonal is 1, all other elements are 0. All right, so what I'm going to do now is walk you through some examples that will illustrate operations on matrices. So this table is summarizing the amount of time someone spends doing various activities. Homework, exercise, computer for 3 people, Andrea, Greg, and Jessica. So we could take this information and we could express it as a matrix. Square matrices in this case. So for D, we would get 2, 3, 1, 1, 4, 1, 3, 1, 2. And remembering, of course, that this was homework, this was exercise, this was computer, and this was referring to the different people, Andrea, Greg, and Jessica. If we wanted to do it weekly, we would have these numbers, 14, 21, 7, 7, 28, 7, 21, 7, and 14. And what I would like you to notice is that W is equal to 7 times D. Times 7, times 7, times 7, times 7, times 7, times 7, times 7. So that's going to lead to our first definition. If you want to multiply a matrix by a scalar, this is how we do it. So suppose we have a matrix represented like this. Capital A is equal to, and then here are all of our elements, ij. K is a scalar from the real number, then we would represent Ka as K times A. So notice what's happened. Ka is the matrix that you obtain by multiplying every element in A by our scalar K. So that's how you would do that, just like we did here. Every one of these got multiplied by the scalar. All right, next thing we're going to take a look at. We'll look at it again through the lens of a problem. So this table is summarizing water sporting equipment produced by a company. This one is for the product made out of wood, and this is for it made out of metal. So we could create a matrix representing W, the things made out of wood. Of course, this would be a water ski, surfboard, canoe. This would be spring. This would be summer. Again, this would be water ski, surfboard, canoe. Again, spring and summer. So if you think about us representing total production, this would make sense. If I add these two elements together, it would be the total number of water skis. Adding these two together, total number of surfboards. These two together, total number of canoes sold for the spring. And we would repeat that. Adding these two is the total number of water skis sold in the summer, total number of surfboards sold in the summer, and this plus this is the total number of canoes. So that would make sense. It makes sense to add those elements because they correspond. They're representing the same thing. We're just first element being made of wood, the second being made of metal, but altogether these are water skis, these ones are surfboards, and these ones are canoes. So that makes sense. That's going to lead to our next definition, sum of two matrices. So first of all, you can only add matrices if they have the same dimension. If they don't have the same dimension, you cannot add them. So how will you find A plus B? So it's defined as the matrix whose elements are the sum of corresponding elements. So we take Aij, we take Bij. So this is the element in the sum matrix. How do we find it? We find it by adding the matrix or the element from matrix A that corresponds to the element in matrix B. And to give you an example, if I wanted to find the element in my sum matrix that was in row 2, column 3, I would add the element from row 2, column 3 in matrix A to the element in row 2, column 3 from matrix B. That's how I would get this element. So I'm going to pause momentarily. Assuming I could see on the side when I looked ahead that I inadvertently had the answers on the next slide. So we had talked about how to multiply by a scalar, how you do that, and how you add matrices. Remember, multiplying by a scalar, you just multiply each element in the matrix or array by that scalar. And when you're going to add two matrices, you just add corresponding elements as long as they have the same size. So what we're going to do first is you're going to do A. Find 3A. Again, a time to ponder pause. All right, resuming to take this up, what we're going to do is I'm just going to start by showing I would like to multiply matrix A by 3. There is matrix A. And then I'm going to show you how I'm going to get the answer. I need to multiply each element by 3. So 3 times 2, a 3 times 1, a 3 times 4, and a 3 times 3. And when I simplify that, I'll get 6, 3, 12, 18. Now, would you be writing this step in university? No. Would you be writing that step in? Doubtful. You'd probably be just jumping to there, but I did want to make it clear how I got that matrix in the end. All right, you're going to try B plus C now. Again, a time to ponder pause. All right, resuming to take this up. Again, I'm going to show you all of my work. There is matrix B plus there is matrix C. The sum matrix is obtained by adding corresponding elements. So I need to add 4 and 1. I need to add the 3 plus 6. I need to add the negative 1 and the 3. And I need to add the 2 and the 4. And when we're finished, that's going to give us 5, 9, 2, and 6. And again, in university, doubtful I'm showing that, doubtful I'm showing that. But I'm just putting this here because I'm worried if I just show you that, in the end, some people might not follow where it came from. All right, now a combination where we multiply one matrix by a scalar and we add it to another matrix. Again, a time to ponder pause. All right, resuming to take this up. Negative 2 times there's matrix A plus matrix B. Multiplying this by negative 2, I'll get negative 4, negative 2, negative 8, and negative 12. And when I add these two together, negative 4 plus 4 would give me the 0. Negative 2 plus 3 would give me 1. Negative 8 plus negative 1 gives me negative 9. Negative 12 plus 2 gives me negative 10. So multiplying by a scalar and adding two matrices, not too terribly difficult. And I'm viewing subtraction as adding. Multiply by -1 and then add. So you should be able to, at this point, to add, subtract, and multiply matrices by a scalar. Now, how do you multiply matrices together? That's the next thing we're going to look at. Again, through the lens of a problem. So this is a table that's summarizing what's happening at a bakery. They sell cupcakes, muffins, and donuts. This is their total sales for April, May, and June. So I guess we could call this a monthly sales matrix. Notice this column representing cupcakes, this representing muffins, this representing donuts. Each row would correspond to a month, April, May, and June. And we also know the cost of the muffins and donuts and cupcakes. So cupcakes sell for $1.20, muffins for $1.05, and donuts for 80 cents. So I've set up a column matrix, which so happens to be the cost. So cupcakes followed by muffins followed by donuts. And now if I would like to know the total, and when I say cost, this is cost, but this actually, a better name would be revenue, right? Because that's what I'm selling them for. So next cost and call it revenue. So I'm going to put R there for revenue. So if I want to find the total revenue for April, how would you do it? Well, you would take the number of cupcakes and you multiply by $1.20, the number of muffins by $1.05, and the number of donuts by 80 cents. So take a look at what we're going to do. We're going to multiply 400 by $1.20, plus 200 by $1.05, plus 300 times 80. So to find this here, element A, actually I think we'll call this R. R1, 1. So our row 1, column 1. We took row 1 and we multiplied it by column 1. I know there's only one column here, but row 1 times column 1. So that times that times that, and that times that. This is going to be row 2 times column 1. So that times this, plus this times this, plus this times this. That's where that came from. And again, it would make sense to do that same process for the third row. So this is row 3, column 1, that times that, plus that, times that, plus that, times that. Now that makes sense in our context here, as long as we're careful when we set these up. We set this up as a column matrix, and cupcakes are coming down here, muffins here, donuts there, and then we lined up a column vector for the cost. And now, not the cost, the revenue again. The cost of a muffin, but it's returning revenue. So our total revenue for each month would be as such: April $9.30, May $1,118.50, and June $900. So this method can be generalized, and this is the method by which you multiply two matrices. So the first thing we have to go over is a matrix that is m by p can be multiplied by a matrix that's p by n. So you have to have a match here, p and p. So a 2 by 4 can be multiplied by a 4 by 5, and it would return a 2 by 5 matrix. So again, the number of columns in the first matrix has to be equal to the number of rows in the second matrix. And in order to do that, this is how you multiply them together. So you're going to create a new matrix, which is C, and this is how you obtain a single element in C. So what is element Cij? It would be A1, AI1, B1j, plus AI2, B2j, plus AI3, B3j, and so on. Now, coming back to this matrix here, how did we achieve this? We did A11 times B11 plus A12 times B21 plus A13 times B31. How did we get the second one? This was 2-1. How did we get 2-1? Well, we started with A21 times B21. That should be a 2 there. I did not. Just pause momentarily. Resuming, I thought I had a typo there, but I did not. So we are going to go A21. We're now going to multiply the second row. So this was the first row by the first column. This is going to be the second row by the first column. So A21, B11. And again, just going to show you how this was written. So we had a 3 by 3, and then we were multiplying by a 3 by 1. So we take the first row, we multiply by the first column. This times this, that times that, that times that. This one would be obtained by multiplying this row by this column. So A21 by B11, A22 by B21, A23 by B31. And this last one would be obtained by multiplying the third row by the first column. So we have A31 by B11, A32 by B21, and A33 by B31. So I hope that little visual helped you understand that. Multiplication is the trickiest of the three operations, but it's not impossible to write in. So what you're going to do is you're going to find the product of the two matrices as written. Notice we're multiplying a 3 by 2 matrix. Whoops. Wrote that backwards. A 2 by 3. The first matrix is 2 by 3. And we are going to multiply that by a 3 by 2 matrix. And when we do that, that will return a 2 by 2 matrix. And an interesting question would be, do we think multiplication of matrices is commutative? If we multiplied this in a different order, we put this one first, we would be multiplying a 3 by 2 matrix by a 2 by 3 matrix. And that would return a 3 by 3 matrix. So it doesn't look like matrix multiplication can be commutative. So you're going to multiply this out. And again, I'm going to explain how you do this. Row 1 times column 1. That would be this element. Row 1 times column 2 would be this element. Row 2 by column 1 would be this element. And row 2 by column 2 would be that element. That's how you're going to get your 2 by 2 matrix. Again, a time to ponder pause. Right, resuming to take this up, and again showing you first row by first column. So 1 times 7 plus 3 times 3 plus 2 times 2. This one here is first row, second column. So row 1 by column 2, 1 times 8 plus 3 times 9 plus 2 times 5. This position is 2, 1. So second row, first column. So second row times first column. 4 times 7 plus 5 times 3 plus 6 times 2. This one is in position 2, 2, row 2, column 2. So row 2 times column 2. 4 times 8 plus 5 times 9 plus 6 times 5. Punching that into your calculator and working it out, you get this matrix, 20, 45, 55, 107. Notice we got a 2 by 2 matrix. And again, if you multiply them in the opposite order, you would get a 3 by 3 matrix. I leave it up to you to explore that one. All right, we'll just do some more practice with matrix multiplication in context, looking at an example. So in our particular example, we've got a building company. They build 3 kinds of houses: bungalows, split levels, townhouses. I guess this is the schedule matrix. It's showing what they're going to build. They're going to build 5 bungalows, 7 split level, 4 townhouses in June. They're going to build 6 bungalows, 5 split level, and 8 townhouses in July. Now, each house they build requires units of material as shown by the material matrix. So a bungalow requires 4 units of steel, 7 units of wood, 5 units of brick, 3 units of glass. Split level, 6 units of steel, 9 units of wood, 6 units of brick, and 4 units of glass. Townhouses require 3 units of steel, 5 units of wood, 4 units of brick, and 2 units of glass. And the last thing is a unit cost matrix that talks about what a unit of steel would cost, a unit of brick, a unit of wood, etc. So unit cost for steel would be it says 200, but this is being measured in tens of dollars, so it's actually $2,000. A unit of wood is 1,600, a unit of brick is 1,800, and a unit of glass would be 1,500. All right, so what you're going to do is calculate the elements of the material schedule matrix. That is, you're going to multiply matrix S by matrix M. And notice this matrix is 2 by 3. And you're going to multiply, I'm going to put a dot for multiply there. You're going to be multiplying that by this matrix, which is 3 by 4. And notice the number of columns here matches the numbers of rows there, so you can now multiply these two together, and you will get a 2 by 4 matrix in the end. Now, you cannot multiply M by S, because if we wanted to do that, we would be looking at a 3 by 4 matrix, and we'd then be multiplying that by a 2 by 3 matrix, and the number of rows, or the number of columns in the first matrix, is not matching the number of rows in the second matrix, so they can't be multiplied in this order. Again, just further illustration that matrix multiplication doesn't appear to be commutative. All right, again, when you work your way through this, you're going to end up getting a 2 by 4 matrix. So you're going to have 2 rows, and there will be 4 elements in each row. So to find this element, it would be the first row multiplied by the first column. This one would be the first row multiplied by the second column, first row multiplied by the third column, first row multiplied by the fourth column, and so on. Again, a time to ponder, pause. All right, so resuming to take this up, as I mentioned, the first element, column 1, row 1 times column 1 is the first element. This is in position 1, 1. So 5 times 4 plus 7 times 6 plus 4 times 3. This is position, we're in row 1, column 2. This is 1, 2. So row 1 times column 2, 5 times 7 plus 7 times 9 plus 4 times 5. This one is row 1, column 3. So we'll have 5 times 5 plus 7 times 6 plus 4 times 4. This one is in row 1, column 4, so it will be 5 times 3 plus 7 times 4 plus 4 times 2. And down here, this is position 2, 1, so row 2, column 1. So row 2 times column 1, 6 times 4 plus 5 times 6 plus 8 times 3. This is position 2, 2, so row 2 times column 2, 6 times 7 plus 5 times 9 plus 8 times 5. This is in position 2, 3, so row 2 by column 3, 6 times 5 plus 5 times 6 plus 8 times 4. And this last one is in position 2, 4, row 2, column 4, so 6 times 3 plus 5 times 4 plus 8 times 2. Hopefully you're getting the hang of that, because that's an awful lot of talking to describe the elements in that detail. If you feel like you're getting it, feel free to fast forward. So that gets me to here. When we punch all of this into our calculator, we get 74, 118, 83, 51, 78, 127, 92, and 54. And I'd like you to think about, like, what is that standing for? Now remember, this was steel, this was wood, this was bricks, this was glass. Let me just take you back just to show you again. That was our schedules matrix, so we were planning on building 5 bungalows, 7 split level, 4 townhouses, etc. And this was telling us how many of each kind of element you would need. So what this is going to tell us is for the month of June, how much steel we would need, how much wood, how many units of brick, and how many units of glass in order to fill this. And this is telling me how much steel, wood, bricks, and glass in terms of units I would need for July in order to construct my, we had townhouses here, split level, I forgot what that first one was, bungalow, right? So bungalow, split level, townhouse. So in order to do all of that work, this is how many units we would need. You can see why that would be useful in the world of business, because now you know what you need to order. All right, let's try another one. I would like you now to calculate M times C and then interpret it. I'm not going to do the analysis up front, but you should figure out what the dimensions of your matrix would be before you begin. Again, a time to ponder pause. All right, resuming to take this one up. So if we take a look, the dimensions of this matrix, 3 rows by 4 columns. I'm going to multiply that by C, and that has 4 rows and it has 1 column. So when I multiply these together, I'm going to end up with a 3 by 1 matrix. So it'll have 3 rows and 1 column. All right, this position here is 1, 1. So what am I supposed to do here? I should multiply row 1 by column 1. So 4 times 200 plus 7 times 160 plus 5 times 180 plus 3 times 150. That's where that comes from. This is in position 2, 1. So multiply row 2 by column 1. And I will get 6 times 200 plus 9 times 160 plus 6 times 180 plus 4 times 150. And this last one here is in position 3, 1. So row 3 and column 1 will be multiplied together. So 3 times 200 plus 5 times 160 plus 4 times 180 plus 2 times 150. You punch that into your calculator and you get 3270, 4320, and 2420. And remembering what these were standing for, so this was bungalows, split level townhouses, this was June, this was July, this was steel, wood, brick, and glass, again, bungalows, split level, and townhouses. And this was our cost for units of steel, wood, bricks, and glass. So what is this matrix representing when we multiply this out? This is a cost matrix, right? And this would be the cost, the total cost of a bungalow. This would be the total cost for a split level. And this would be a total cost for a townhouse. Because what have we multiplied together? We have multiplied the number of units required to build one of these, right? That's how this was working. So a bungalow requires 4 units of steel, 7 units of wood, 5 units of brick, 3 units of glass. The split level requires 6 units of steel, 9 units of wood, 6 units of brick, 4 units of glass. Coming down to the townhouse, it requires 3 units of steel, 5 units of wood, 4 units of brick, and 2 units of glass. And of course, these are the cost of those corresponding elements. So what we've got here is a cost matrix, and it's representing the cost of the materials for each type of house. In tens of dollars. Remember, that was in tens of dollars. So the cost of a bungalow is $32,700 cost in terms of materials, no labor there. The cost of a split level is $43,200, and the cost of a townhouse is $24,200. I'm just trying to help you gain some perspective there. All right, one last thing for you to do. Calculate S times MC. So we have got MC here. We have got S here. Now we've determined that matrix multiplication is not commutative, and we're actually going to do S times MC because we already have MC. Something interesting to explore might be for you to find SM first and then multiply that by C, and this will test to see whether matrix multiplication is associative. We've discussed that it's not commutative. All right, so you're now going to multiply S by MC, and then you're going to interpret what you get left. And this will be our final time to ponder pause. Zooming to take up this last question. So the dimensions of S are 2 rows by 3 columns. We're going to multiply that by MC, and MC has dimensions 3 by 1. So this is going to return a matrix that is 2 by 1. So it's probably a good idea to decide what you're expecting. So I'm expecting 2 rows, 1 column, so this is a column matrix. So where are we here? We are in position 1, 1. So we should be multiplying row 1 by column 1 in order to get this number. So notice we did 5 times 3270 plus 7 times 4320 plus 4 times 2420. This position here is 2, 1. So we should be multiplying row 2 by column 1. So row 2 by column 1. Notice we have 6 times 3270 plus 5 times 4320 plus 8 times 2430 Punching all of that into your calculator, you'll get for SMC 56,270, 60,580. And remember, these would be in tens of dollars, right? Because these were in tens of dollars. So if we want to know the actual cost in dollars, so 562,700, we'd be 605,800. Now, how would I describe this? This would be a schedule materials cost matrix. What it's going to do, it's going to show the total cost of purchasing materials for all of the homes that we're building in the month of June and July. So remember what this is doing for me here. This matrix, we said, is, just jump back here to show you, it's giving us the total cost for each house. So the total cost of bungalows, split levels, townhouses. So we can write that back here. Bungalow, split level, townhouses. And remember, jumping back here, bungalows, split levels, townhouses. That's how this matrix was set up. Whoops. Better if I write it on this one. Bungalow, split level, townhouses. So you've taken the number of bungalows multiplied by the cost of a bungalow. You've taken the number of split levels, you multiplied by the cost of a split level. You've taken the total number of townhouses, you multiplied by the cost of a townhouse. Then for the second month, which was the month of July, you've taken the total number of bungalows times the cost of each bungalow. You've taken the total number of split levels times the cost of a split level, and you've taken the total number of townhouses times the cost of a townhouse. So now that we've seen that in action, that makes sense that this is a schedule materials cost matrix showing the total cost. What will it cost for in tens of dollars? This is in tens of dollars. In tens, right? So we need to multiply that by 10. So in tens of dollars, the total cost of purchasing material for each month. All right, that brings us to the end of this lesson. If you made it to the end, once again, thank you for watching. Don't forget to smash that like button. And as always, take care and stay safe.